Good morning. After a few little incidentals that we had before we got started here, we're up and running. This looks like a day where it's maybe going to be a mixture of warmer and colder. I'm not really sure. I see this. It looks like winter storm weather, actually. If you look.
Rain right now.
Yeah, and I didn't wear the right layer, but oh well. I don't have to go that far. At any rate, a lot of things have been happening. I tried my hardest to get both problem sets graded, and I just had to fall off it last night and switch to getting ready for lecture. But I did get problem set number 1 returned to you, and on the home page here there is a link, and I talk about what I just said about how I tried to get through. I got a third of the way through set number 2. I've gotten bogged down in some details of formatting and things. I'm glad you're all trying out Jupyter and Python in various forms. I expect that you'll be trying different forms of turning in your homework, and I'm going to talk about that when we get into Jupyter this morning in terms of how not to do what at least one person has done, made it impossible for me to grade their paper, because it's like a sentence that long. It has about 30 words in it, and then if I try to look at the whole sentence, it's microscopic, literally. I mean, it's just impossible. And I don't know how you can do that, so I'm going to show you how to get that straight away. In terms of the histogram, though, I'll just go to this link. This is going to be a cumulative histogram, so right now it's just showing you what happened on set 1, and I'll explain some details on what happened. But what my plans are, my plans are always to use a spreadsheet type program to create histograms after the data has been stored and processed. So right now in the homework category we'll have problem sets. I've decided to abandon the idea of the quizzes, but we'll have problem sets, and as each new problem set comes in, the spreadsheet just calculates, the new numbers come in, I renormalize it by the new total, and then it's based on 100 points. So if you look at the paper I gave back to you, the first paper I think was worth 25 points, but it's now scaled up by 4 effectively. As I add them in, they're all weighted according to the number of points, and if there's bonus points or things like that, numbers can go over 100, which is why the scale here actually shows it going over 100. I didn't give any bonus points out this time, but I'll probably do that at some point. At any rate, this just shows you, and this is because we're not turning in a lot of problems, just because I've got 17 papers, I just don't have a lot of time to grade. I mean, I'm putting in a large amount of time as it is to grade those 17. It's just I have to do less problems per person, and use that to your advantage and disadvantage, I'm sorry to say, but use it to your advantage, and that put all the energy into those problems. We're going to look at one of the problems from assignment 3 today in detail in class because it's important in the lab. Unfortunately, though, 3 people in the class did not read the assignment, and they worked problems that were the wrong problems, either the drill problems or, I don't know. The 3 people that made this mistake, they were not even consistent in what they did wrong. I mean, I had like a bunch of linear systems problems. I don't know. It was just confusing to me, and that's like starting all over again, and the problems are different, so I just simply was very generous. I gave 50%. So there's 3 people that they got 50% effectively for working problems that were not at all what were assigned. I know some of you are in here. I don't want to necessarily point you out, but I'm not sure what happened. If you want to tell me how you got confused, because the majority did not get confused. The book has got the drill problems, and I assigned them on set number 2. I assigned them on set number 3 again. They're actually very good, but when I originally taught from the book, I used just the regular problems, the ones that say problem as opposed to drill problem. It makes sense in a lot of ways. It almost seems like you're going way back in K through 12. Doesn't that sound, the idea of a drill problem, doesn't that sound like K through 12? Like we're going to drill you on this, and you're going to, well, when I was in graduate school, I had an advanced calculus real analysis class, and the professor made us work problems on the board. That was what we had to do as graduate students. What was challenging about that is you couldn't just sit there and watch, because you also had to critique. As if you weren't up there doing a problem, you had to critique and say what's wrong, and the professor would be as equally harsh on this class if they couldn't identify, was it a good proof, was it a bad proof, or whatever. But you know, different things happen at different times in your life. But the bottom line is this will step over time. So that's why there's blank paper down there. The next histogram will be sets 1 through 2, and then it will start unfolding and unrolling, which is what I expect to happen. It's kind of like convolution. What does convolution have a tendency to do? It tends to smooth things out, and it might spread out more. In the case of the statistics and the histograms, what happens over time is that they do the opposite of that, not convolution, but they still morph, and they will tend to get more clustered, and they will tend to get shifting up higher unless something really awful happens, because there's always an adjustment period. So you can message me on Slack or talk to me after class if you want to. I'm going to back over to here and just go into the lecture stuff and then into Jupyter eventually. So switching gears now and going with where we're at, I also pointed out yesterday when Sam pointed out to me, thank you, Sam, that I had a date and a day wrong. The 20th was on my mind as Friday, and I think we're heading for that, no problem. If I feel like I need to veer off of that and give you more time, I will, but I'm also trying to be cognizant of where we are in the material and getting into the comms material and getting towards our exam 1, which, based on what I feel is going to happen today, I guess I can go ahead and just look at the calendar here briefly and say, I visualize that we will be wrapping up chapter 2, or what I want to do out of the chapter 2 today, maybe starting chapter 3 in the notes and in the book. And that means that there may be 1 or 2 problems on set number 4 that are from linear systems theory or something at the end of the chapter that we're going to look at today. But we're ready for the first exam, which means I would, you know, those 2 dates right there are kind of on my mind, the 3rd or the 10th. So we're going to not have a final vote on it right now, but I want to get some ideas, as I'm just throwing this at you right now, 3rd or the 10th. I mean, and some of you are going to take it in the testing center, or at least that's what you told me at the beginning of the semester. But the way it will work is I won't dedicate the whole lecture period to an exam. That would just be way too much time, and you'll get frustrated if I give you a lot of time and a lot of problems. That's just unnecessary. I'll lecture for a while, a shorter time to the first break that we have. Normally I have the break at about midpoint, but we'll have a lesser amount of time, and I'll stop and I'll say we're having the break. When you come back, be ready to write the exam. And those of you that are going to go do it at the testing center, and they're not all of you in that category are here today, but you will then leave the classroom at that time, because you'll be expected, or I'll be expecting that you'll be going to take it at the testing center. And those of you that are in that category know what I'm talking about. If you've never done that in your life, don't worry about it unless you want to apply to the disability services. And then we'll carry on from there. And of course, the idea of having the exam being in the latter portion of the class is that we'll wrap up the exam and you'll take off. And if you finish early, you leave early. I think that makes the most sense. I don't like the idea of saying we're stopping now, we're going to go back to lecturing. I'd rather you just fade out and head out from here. Any questions about that? I will have obviously old exams posted, but the 3rd can work. Nominally, if I do give a couple of problems that wrap up chapter 2, and that might be all I'll do, I'll have those due on the 27th I've only got one or two that I'm thinking of right now, and maybe I'll just leave it at that, and I'll have a short set number 4 so we can get on, be wrapped up with chapter 2. And then we'll be into amplitude modulation. But if I ask for a show of hands, for those of you that are here, does anybody have a slanting one way or the other? This is, by the way, it's also called a benevolent dictatorship. What does that mean? It means you can vote, you can give me your ideas, I still have the final vote. Does that make sense? So, any thoughts anybody has right now, what day they'll be leaning towards?
For the third, yeah.
You're thinking the early one?
Yeah.
Most of you probably have other exams lining up pretty soon, so, and that could happen today, right, or this week, so. Okay, okay, Sam, you're saying early. Anybody else?
It'll be based on the homework problems, right?
Exactly,
Okay.
exactly.
So just do all the homework problems, even the ones we didn't have to turn in.
Exactly. And the quiz thing, remember I told you that I was going to put out old quizzes that I wasn't using. I'm now thinking that those might just turn into extra study problems for the exam too, because those are typical of problems that would be on an exam, and that'll go into your stack of stuff that you could be looking at for the exam. Question?
Did you say at some point that you had practice exams posted from like past exams?
I will have old exams posted, yeah. There's actually a spot for them on the website. If you go down into here, is this the right class? Yeah. They're just not posted up here yet. And those dates look like a long time ago, but I haven't taught the class for a long time, so I don't have anything newer than 2020, and that was COVID time.
Okay. And then should we expect the content in the problems to be similar to the ones on those exams?
Yes, mostly. And what I'll do is the day before we have the exam, at the end of the period before the exam period, we'll have a review session where I'll pull up the old exams. They'll be under password, PDF lock, and we'll look at them in class a little bit, and you can ask questions on them. So.
Oh, so will we be able to access those on our own time?
Yeah, exactly. Yeah, and that's what I want you to do, and that's why I was mentioning the old quizzes that I didn't put up there. I could put up 3 quizzes in a row. I might be able to find solutions for them, or I might sit down and find time. That's kind of my challenge right now, but okay. So most of you don't want to commit, but there's a leaning towards the 3rd, is what I'm hearing right now. You can always push to me on your Slack channel to me what your thoughts are. If you want to make a proposition to the whole class, push a message out to the whole class, like this is why I want to have it early or something like that. There's something else that I guess now that we're looking at calendars, and I keep wanting to sit down to do this, this is maybe going to be shocking to you, but I'm going to tell you something that I have been holding back on because I just haven't felt I had the right time, and that is when I agreed to teach this class, Dr. Trimboli, who asked me to teach it, it was moments before, a month or so before I even knew that Mark Frank had passed away. Yet Mark Frank had always said, will you substitute for me if I need you? And I said, if I'll be here. And he said he would substitute for me if I needed him. Well, then when I later found out he was no longer available, I thought, what's going to happen if I need a substitute? And then Dr. Trimboli said he wanted me to teach the class, even though I had a Viking cruise trip planned starting at the end of April, and when I get back on May 5th, I think it is, or May 4th. So that means I'm not going to be teaching every class. And I've had some thoughts on that, though, and the reason why I'm bringing that up right now, let's go into March. Spring break week is these days. Does anybody know for sure? It's generally been.
It's last week of March, yes.
Last full week, right?
It's last full week of March.
Yeah. So if we dial ahead into April, this is the day I return and I leave I think I leave on the 17th, if I'm not mistaken, flying out. So we have the 21st, 28th, and the 5th of May, and I think finals week, if I'm not mistaken, is probably this week. Does that sound about right? I mean, we have to nail that down. But if, and this is why I'm talking about it now, it's a huge if, because I generally don't go anywhere for spring break, even when I was a regular faculty member. I would go on a cruise or something like that, fun with my wife, now that I'm not a full-time faculty. And I did last year, and I'm going again this year. So what could we do to mitigate the discontinuity between me and whoever comes in to replace me for a few lectures? We could do something during spring break week. I would be willing to come over here and do it myself. Most of you might say, that's crazy. I want that week off, or I'm going to go somewhere in the world. I don't know. But I'm just putting that bug in your brain. I'm not trying to force your hand. We could have a double lecture, twice a week. I don't know where we would do it, but I could investigate that. Does anybody have any thoughts, immediate thoughts? Again, you can write to me on Slack on the private channel on what this news means to you. I'm not going on my trip because it was paid for when I was asked if I would even come in and teach. It's like, no, I'm not going to not do that. What's that? Just watching old video lectures? See, I'm not going to be able to hand out exams. I'll get somebody will surely proctor. I think Dr. Trimboli actually realizes that he's got to do this at the very least. And yeah, having an exam made up and that sort of thing. I guess let's just keep lecturing today, but I want you to be giving it some thought so you can see what we're up against, and all of you might have a different angle on it, but I'll gladly take ideas and suggestions about how to manage this. Mark was who I thought I would probably get. And this is kind of crazy to say, but Dr. Trimboli was so excited. He said, I want you to do this. And I said, but I can't finish it. Oh, that's okay. I want you to still start the class and do it. And I thought, Mark probably will take over, but why aren't you asking him? And then, of course, I told you the first day of class, I learned later in November when his wife called me, he had passed away. So it's just like, every time I think about it, I just kind of get emotional about how this was so difficult, because I helped train him on teaching the class, and he used my course materials and stuff. But we have to move forward, so we can't dwell on what could have been. It's what's going to be is all we got to choose from. Okay, so last time we were talking about power spectral density, and this is kind of like the final result we came up with for our math model. We have a waveform. If we can get its autocorrelation function, we will get a means to get the power spectral density through the Fourier transform or the autocorrelation function. So we have a few examples of that we've had in the book and are in the homework problems that you have. They're the cases where we have a sinusoid. A sinusoid is just plain easy to always work with. We can always get the autocorrelation function from its time domain waveform. We can always Fourier transform sinusoids into delta functions. For the PN cogenerator, which we looked at a little bit, and we're going to look at a lot today, we have the autocorrelation function for that pseudo-random sequence. It ends up being a periodic waveform once again, and we can get the Fourier transform of the autocorrelation function. That's huge in the lab right now, and I'm going to be going through problem 7 on the homework this week. I've already got it to push out here, basically giving you the solutions, because I'm wanting to help the lab for sure on that one. What about other waveforms? Well, the other waveforms are mostly into the category of random processes. So we don't have the same flexibility in this class because I'm not teaching you random processes, but we can make some analogies, and also I can show you some more special cases. So we're not going to go totally overboard on power spectral density, even though it's used in the measurements in the lab all the time. We just have this formal definition, and we think we have to get it somehow. So what will I do if I'm doing this in a scenario in work that I'm doing? I will generate a simulated waveform, x of t, as a discrete time waveform, and then I will use a technique of power spectral density estimation on the waveform itself. And you've already seen that. The very first Jupyter Notebook did that, and I'll do it again today. It's in the notes in the Jupyter Notebook for today as well. So that is probably the most common way of doing it in a computer model. And of course, in the lab, we have the instrumentation in the lab. So having everything tied precisely to an achievable or hands-on mathematical model is not always possible. And as time has marched on, most everybody is pushed more often to the simulation realm. And I'm pushing you in that direction too. That's why I'm pushing you on Jupyter so much, because I want you to just be able to say, hey, I'm going to model this, and I'm going to get something that I can get answers from. I'm not going to worry about every last mathematical detail, because things get so complicated if you go up down that path that you can't do it all. You end up resorting to simulation. And I don't think that's a new concept for you guys either, because when did you first learn about LT-SPICE, for example? Okay, so electronics 1. Have you relied upon that often, or enough to say it's very tangible? It's like, I can do something if I can do a model in SPICE. So that's kind of where I land on that too. So the other big thing, though, that we did last week, let me see. We looked at energy spectral density too, but I was going to say, looked at PN sequences. Another big result that I had presented, this has a bunch of math equations in it, but it distills down to this fundamental result. It says if we have something that has a Fourier series representation, some other type of periodic waveform, we can get to it directly through its Fourier coefficients, just take the magnitude squared. And most people would tend to say, yeah, I should be able to do that anyway, because if I have a Fourier coefficient in a Fourier series, that's like an amplitude of one of the harmonics. I take the magnitude squared of that amplitude, and if I'm in a 1 ohm system, that gives me power immediately. Agreed? I mean, we always have this fabulous 1 ohm system, and it buries away the impedance. Those of you in the lab are learning how to handle that too, with the 50 ohms and everything. So we have this to fall back on too, and this is used in the lab quite a bit. So let's just take another example, and we talked last time about how PN sequences, pseudo-noise sequences, are used a lot in testing digital communications. They're used in ranging to get ranges out and back to a satellite. They're used in ranging to get our geolocation on the Earth with the GPS system. They're just very, very useful. They're used in other applications too, synchronization, frame syncs, other things that happen in digital comm that are going to unfold more. I guess the other example I gave last week was geolocation using a complex ambiguity function. That was an interesting problem, right? I think makes me think about how I could have said more about that, but that was this problem over here. I added some more stuff to it so I can animate it, but I didn't really explain this really well, and it just bumped into my head again. Remember when I showed this last week, did everybody capture what we were looking at here? We're looking at a three-dimensional plot. This is looking at it as a surface, and we're using color to denote the height above the floor of the surface. So the correlation peak in this case, rather than being an autocorrelation, it's a cross correlation between a reference waveform and a waveform of interest to us that's been captured, and we're looking at the correlation in 2 dimensions, both time delay and frequency offset. And this is like the 2-dimensional view of the autocorrelation function of the PN sequence, which has a nice triangular peak to it. This has got some blobby shape to it. It maybe looks more like a Gaussian bell or something like that, if we were to look at it in a surface plot, as opposed to the image type plot here. So the PN sequence is one that is periodic. When you run a shift register sequence like this, you get a periodic waveform, and this shows it. An example for 7 periods, 7 clock periods is the period, or m times t in general is the period of the waveform. And the taps are chosen to give a particular feedback combination to create what's called a maximal length sequence. I'm not going to jump off into that, but if you were to just go into Google and type M sequences, you would probably get a Wikipedia page or some other site that would talk to you about sequences such as PN sequence. Pseudo-noise is what the PN stands for, but there's various types of PN sequences that are used. What was another example that just came back into my head? Nobody's using 2G anymore. Does anybody have a 2G cell phone from Qualcomm anymore? No. But that you got a PN sequence assigned to you, or a portion of a long PN sequence was assigned to you through your SIM card, and that's how you were identified and correlated out by the base station to know this guy's going to be transmitting to me with a PN encoding on top of his data, and it's going to correlate you out with that PN data to find your data bits and your information, and that was assigned through your SIM card. Okay, so this is a given then that we have both here in the lecture and in the lab, that for a PN sequence that has amplitudes of plus and minus A, and that's what we have going on in here, this is what the autocorrelation function looks like. So if we have that in our hands, we have access to the power spectral density, and we can study and appreciate what goes on with this type of waveform in terms of the spectral occupancy of it. So I'm going to drill into this a little bit right now, and this is problem 3 or problem 7 in the homework. So in order to Fourier transform this, knowing that this is also a periodic autocorrelation function from a periodic time domain signal, this will become a line spectra in the frequency domain, in the power spectral density domain. So we just want to Fourier transform this, and this will appear when the solutions go up for set number 3. It's not one of the problems that you're turning in. So we have PN generator. So I'm doing this so that you can see more of the intimate details of applying various Fourier transform properties, but also for those of you in the lab, I think it's useful to get this, grind this out a little bit more. This shows you the results for plus and minus A amplitude. Just to jump back over here for a second, if we have to work with a waveform that's been level shifted, that would mean that we're going to say add a value of A onto a waveform. So plus and minus A might be the amplitude, or plus and minus 5, let's say. I could shift that up and down by adding a constant to it, A. And the end result of this theorem or property is that the constant term just shows up in the DC component. So these 2 pieces here are the DC component. The autocorrelation function, that's a function of tau, the time shift or time lag, just passes right on through. And we also talked about how the autocorrelation function is blind to time shift in the waveform. This actually showed up in the set number 2 problems for Fourier series of waveforms that I marked a bunch of papers on that. It doesn't matter, say, in odd half-wave symmetry if the waveform is centered on 0 or whether it's centered a little bit this way or that way. If it's odd half-wave symmetric, it has that property that the even harmonics are 0. Remember, and many of you, the papers I've graded on set number 2 clearly identified what I was looking for, and that is if you phase shift or time delay a waveform, that does not alter the spectral amplitude. It only matters with the phase of the spectrum, right? I mean, I was very happy when I see people that just wham, you have it down on the table, you totally get it. And what you should also be totally getting is we're not really usually as interested in the phase in a spectrum at all. The power spectral density is kind of like the elevation beyond just the Fourier transform, saying we're going with the power density as a function of frequency, and that doesn't have any phase in it either. And it follows from the fact that the autocorrelation function does not change with time delay. The cool thing about COM waveforms and the necessary thing about COM waveforms is they arrive at us wherever we're standing in space, and we don't really have control over the exact phase of the time delay. We're moving around actually all the time. So now in synchronization properties, we do have to deal with it, and that's dealt with in symbol timing. And we also have to deal with the phase shifting of the carrier, and we'll get more into that into chapter 3 and then on into chapter 4. So at any rate, back over here to this problem, how would you Fourier transform this? First off, we should go back to this theorem which we talked about last week. And trust me right now, there will be an exam problem on this on exam 1, because this is like so valuable and so important to understand that if you have a waveform that's periodic, you can get at its spectrum by just getting the Fourier transform of one period of that periodic waveform and then factoring in the time or the period Ts. This is just the notation, the way it appears in the book. Ts would be Tp, let's say, or the period. But at any rate, this becomes really valuable. So in order to Fourier transform this waveform, I just simply look at it and I say, okay, how can I decompose that into a fashion that is manageable for me? So the way I chose to do it, and the way I recommend, but I can't make your brain work the way my brain works, because we're all different. We all see things somewhat differently. But the way I like to do it is I will just take the bias out of there. So I will pretend that that waveform is sitting at 0, because that makes the triangle part really easy to handle, right? The triangle function just starts at 0 and goes up to its peak. So I'll just pretend it's gone. And then, so I'll have a new waveform that's the triangle waveform that's sitting at base of 0, and then I'll add a constant into that. The constant is called C in this case, but if you look at the waveform, that offset from being at 0 is minus a squared over m. So that's the constant value. And then the rest of the waveform has to be the total amplitude, and that's the amplitude in going from the base up to the top of the triangle. So that's going to be a squared plus a squared over m. And that then is right here, a squared times 1. And then the amount that it hangs below is 1 over m times a squared. And then we have a triangle. If we're thinking of it as one period, the period centered on 0 is tau over t. And t in this case represents the width, or the half width of the triangle. So that's like from here out to there. So that's t. So now I just Fourier transform that. Well, I put it all together now. I then Fourier transform it term by term. So I have a constant minus a squared over m And then I have the a squared times quantity 1 minus, or 1 plus 1 over m. And then I'm just writing the repetition of the waveform up and down the time axis as a convolution with a delta function. I didn't have to do it that way, but this brings to mind the fact that what does the delta function do? It just keeps picking that waveform up and laying it down again at offsets at multiples of mt, and mt is the period of the pulse train. So when I Fourier transform it term by term, I get this first row of math, which is the DC component, the minus a squared over m, and then I get the component with the sinc function squared from the triangle, and there's a little nuance in here that let's see, I've got to remember how to bring that back in again. We have this Fs in here. See if I can get my pencil to work. So we have to put that in, and what is Fs in this case? That is going to be, sometimes I'm not really happy with the way I can work this stupid thing. Too many knobs on it. When I grade papers, I'm using my Apple Pencil, and this rubber tip thing is just like so inferior to my Apple Pencil that I get kind of totally uncoordinated with what I'm doing. And it's grouping all those together. I won't worry about that stray mark. At any rate, Fs is what? It's 1 over the period. So the period is mt, so Fs is that, 1 over mt. So I have to get that inserted in when I do the Fourier transform. So I have the Fourier transform of p of t is going to be the sinc squared of n over m, where I've already replaced f by nt over m, and then I have capital T inside of there. So I guess what I skipped over here is when I originally go with this guy right here, I'm going to have a t times the sinc squared of what? F times, let's see, I get that wrong. Ft, and t again is from the triangle, so that is sitting right down in here, but I've replaced f by its sample frequency, which is 1 over mt, because that's where the delta functions are hitting. They're hitting at multiples of mt, and then in the frequency domain they're hitting at multiples of 1 over mt, so that samples out to be just n over m, and then the t that was sitting out in here, which is 1 over mt, the t that was sitting in here goes and joins forces with let's see, I had this in my head a second ago. I have to have 1 over Fs, so I have to have 1 over mt out in front. So I do have 1 over mt out in front, and the t that was from the sinc function, this guy right here, and then another t that was part of the Fs, 1 over mt. Those two t's cancel, and I'm left with that in the denominator. I don't know if that was clear enough or not, because I felt like I was going in circles there for a moment. So that's our Fourier transform, and the only cleanup we can do on it, which is kind of a nice thing to do, especially for those of you in the lab, is to go ahead and just take and bring all of the DC components out onto themselves and just have the sum over the k, all the non-DC terms. In other words, n does not equal to 0, is just whatever is left over. So when I do that, I'm going to get, and this, you have to think about how it is that I'm going to do that. I had minus a squared over m to begin with, but then what happens on this first term on the top side, when I set n is equal to 0, I'm going to get sinh squared of 0, which is 1, right? And then I'm going to have the remainder of that. So I'm going to have, a squared over m times 1 plus 1 over m. And that 1 in here is sinh squared of 0. So now all of that stuff condenses down to a squared over m. Why? It's because this term right here is embedded in these two terms, so they're effectively getting annihilated, so we're left over with an a squared over m squared. So that's the DC component that remains. Does this seem tedious? It should be kind of tedious looking, because that's just the way the math ends up being. That's why carrying the intimate math details through for every special case that you have in your life, you end up just saying, I'm going to simulate this because I understand that these types of things are going to be happening. So at any rate, I have the stuff that's sitting out here, and this is what the spectrum analyzer shows you. It's showing you the non-DC components. So for those of you in the lab, you've been looking at this, I think, already, but if you haven't, you will be looking at it soon. I then simulated a couple cases down here. I just simply used the line spectral plotting function to just show you what it looks like for a 3-stage where the period is 7 bits long, or a 5-stage where the period is 31 bits long. And what you see in the spectrum analyzer in the lab is you see spectral lines. You only see the positive half, and you see it scaled so that the dB values are, larger, because we take and fold over the negative frequency to the positive frequency on the spectrum analyzer. But they're all spectral lines like that. And then this is just the shorter length case where they're further apart. So the bit period, though, sets the spacing what? In this case, the bit period sets where that null occurs, and where that null occurs. The individual spacing of the lines is controlled by the period of the code itself, so that is 1 over m times t. So those are closer together, whereas the nulls of the spectrum occur related to, just like in a pulse train, the pulse width, the bit period itself. So it's 1 over that, which in this case, the way the numbers worked out was 1 megahertz. So this would be like a baseband version of a bit stream at 1 megabit per second is what it would be. And then the fact that you can see spectral lines in there has to do with the fact that it's periodic, which I should pause on that for a moment. Why do we always see spectral lines? Think back to the first week of class. We were talking about Fourier series, right? Periodic waveforms always have spectral lines making up their spectrum. So the fact that we just have this PN code, it's periodic, it's going to have spectral lines just because it's periodic. Does that make sense? These are clues. I mean, these are clues that I don't mean so much in the homework, but if you're working in the lab on a project, you're a test engineer and you're testing something, you say, I know I'm using a pseudonoise sequence. If I zoom in to that spectrum, I should see discrete spectral lines because I'm using a periodic sequence behind it. So what I'm going to look at here at some point today is I'm going to say, what happens if the bits are not periodic, but they're random? What do you think happens if I have purely random bits? What's going to happen? This is random processes, and I'm just sort of leading you along saying intuitively, what do you think it happens? If it goes from a period of 7 bits to 31, and notice what's happening. The lines are further apart here because the period is shorter. So the lines are further apart. It's 1 over mt, or 1 over 7 times t, or 1/7 of a megahertz. Here it's 1 over 31 times 1 megahertz is the spacing of the closest spacing of the line. So what's the trend? Longer period, the lines should get closer together, right? So in the limit, this is a good, engineering math idea, right? Mathematicians like in the limit to the infinite degree of math preciseness, but from an engineering standpoint, we can just say, well, if it becomes very non-periodic or random-like, it's just going to not have spectral lines anymore. It's just going to be a solid line, and I'm going to demo that to you. So purely random bits in a bit stream would be just a smooth sinc function, or sinc squared in this case, for the Fourier transform of a triangle. So that's the only difference it makes. It just requires the understanding of random processes. But all that will happen here, oops, wrong page. All that happens here with our basic theory that we were looking at, that autocorrelation function will not periodically be a triangle wave. It will just be a single triangle. It happens once, because if it's random, it doesn't have another one that repeats. It only occurs once and then goes to 0. So we'll be Fourier transforming a triangle, and we'll just get a sinc squared, and the spectrum will be continuous. Is that kind of making sense? It's very cool, actually, the way this all works out. But the autocorrelation function, just tells you how the waveform's correlated with itself. And if the bits are random, like my hand represents my bit train, and this is like a marker on it, it lines up, I get a strong peak. If it just gets further and further apart, it's just seeing random bits, and it's not seeing any likelihood, any likeness to itself again. And the autocorrelation function just decays off to 0, and it's gone. Kind of like some application you might think of in statistics, correlatedness of some statistic or some measurement. As we get more and more disconnected, we're not correlated anymore. Okay, so I've talked about that example. Here's the PN function generator. We looked at this again. I chose to go on to say, let's just do a pure simulation of the PN generator idea, where I'm just going to generate one period of the PN generator, and then I'm going to process it into a waveform and then get at its spectrum directly from simulation. The first calculation here was from a line spectra, but then I next move on to just doing a pure simulation. So I want to look at that in more detail. So let's jump off the page here and just look at the differences. This is a simulation result, and the result above is the same direct Fourier series type analysis, where I'm just going to find the Fourier coefficients for the periodic triangle-shaped waveform. By the way, remember the very first homework assignment was a triangle that repeated itself, so it was kind of like leading up to this moment of looking at PN code generators. So things have a way of working out. It wasn't my forethought, it was the author of the book that said, I've been here before, I want to lead them down a path. And you're college students, you know that you start someplace and you go down a path of ways, and then you stand there and you can turn around and look back and say, I came from here. Do you suppose I did that on purpose? Authors of books do that, right? I think the word is called pedagogy. It's just saying you have a method to why you're doing it a certain way. but also makes me think about backpacking and hiking on a trail and not getting lost. What's something that you always do if you're on getting way, way back? At least something I do. I stand there and I turn around and look back because I get a perspective that's different. Like if I'm going to take this trail back out again, I'm going to see it turned around, and he better have some sensibility. Has anybody ever gotten lost when they're backpacking or hiking? I don't recognize where I've been. I mean, I was a scout leader, and I had my sons and other boys that I was out in the backcountry with, and I always found it really valuable to look back and just see what does it look like, because if I go back, I want to know where I came from. I sighed to myself because I got confused for a moment when I had to go off the trail to do my business, and I came back onto the trail. I'm like, which way did I come from? And I started down the trail in the wrong direction. I kept walking. I kept saying, no, I've been here. This is not right. And I turned around, and then finally I could see the people because we had all stopped to take a break. And so your example, you found where you were going eventually?
Yeah, I hit a fork on the road. I went the wrong way.
Okay.
And yeah, so about a mile, I'm like, this is wrong. So I went back.
You were a little bit nervous at some point, though.
It was beautiful, though.
Yeah?
It was. It was definitely a cooler route. But
The rest of your group maybe was nervous that where did you go to?
yeah.
So, or if you had an avalanche or a rock slide. I'm thinking of sometimes I was on Long's Peak a few times. Some of you, have any of you ever hiked up Long's Peak in Rocky Mountain National Park? It's a high class level, whatever the system is, where you're on boulder fields, you're on ledges, and then you're scrambling around, and then there's an area just before you get to the summit called the Trough. And the Trough is this long, narrow thing you're climbing up that has boulders scattered around in it, and the boulders can come sliding down because there's water and stuff in there, and people have gotten killed up in that area. Actually, I didn't know that until I was up there and coming back down, and a guy said, yeah, I came across a body and so on, and it's like, it's not a place you want to hike by yourself. But the Trough can have rocks move around on it, and they're not small rocks. They're rocks that will, crush you if you get in their path. So that's a very kind of a thrilling hike. It's an extremely popular hike because Rocky Mountain National Park seems like a place to go visit, and people seem like it must be safe to go on this trail, right? There's always hazards, so you got to be alert to that. So the first thing I'm going to do before we look at this example in more detail is just do some basics, and I have some interesting things here in the notes. And in particular, I'm looking at this section here where I'm going to use a function that's in the SS module called pngen, and I think it's now lowercase pngen, but we'll check it out. And then I filter it with an upsampled version, and these are DSP speak things, so I created another notebook over here that I'm going to use to kind of walk through that. So I'll push this notebook up here, but this, how could we create a bit sequence that looks more or less analog-like that we want to use in simulation from scratch? So we have, and I'm going to be doing this live, so we have the SS library, and we have pngen. That was right. My co-author, Charant, who teaches the lab for you guys, he made everything Pythonic, I guess is the term. He lowercased a lot of my function names in the library. So pngen, whenever you type into one, you can always go Shift-Tab. What does it do? It generates so many bits. So I'm going to go with a 5-bit generator as my second argument. But then I'm going to say how many bits do I want. I'm going to go for 50, let's say. So there are those 50. If I was to go here, create a new cell below that and just plot that. So I'm going to say PN5 is that guy. I'll just plot it right down here. And if I was to put another plot on here, and I'm going to put red dots on all markers on all the points. So there's my 50 bits of a bit stream that has amplitude 0 and 1. How would I make this look more like a waveform? This just looks like zeros and ones, like in a computer code or in a microcontroller waveform. How can I make this have a fidelity to it? I can stretch each of those pulses out. So what I was doing in that part of the notebook there, I was going to say, okay, let's upsample that waveform, and what I'm going to do is I'm going to use signal L filter. Well, let's take it one step at a time. PN5 upsample is just going to be ss.upsample. I'm just hitting tab there, and this tells you that what upsample does is it places L-1 zeros between each input sample. You see this when you take modern DSP. I think when you had 3205, you probably don't do any multi-rate processing. And multi-rate processing is the bread and butter of systems implementation, modeling and implementation these days. So what the upsample is going to do is if I take PN5 and I upsample it by 10, and now I choose to plot PN5 underscore up, I can hit tab again and it will say, yep, you already have that variable you defined. Hit tab again. Use these things whenever possible because it keeps you from making typing errors, and then you get errors because Python says you have a variable you didn't define or something like that. So now I'm going to upsample it by a factor of 10, and now we see something that looks different. What we're seeing is between every one of these samples, there's 9, 10 minus 1, 0 samples stuffed in between. So this is staging us to create a waveform through what's sometimes called impulse train modulation. So we're going to be taking and filtering this signal that's been upsampled, and we want to fill in all of those 0 samples with the very first sample in each string of 10. So all I have to do now is signal.lf. I'll use the L filter function from the scipy.signal module, and I'm going to explain to you here. I'm sort of filling it in backwards, but I'm going to go over to here. I can always do Shift Tab. What is this L filter? It filters along one dimension, either an IIR or FIR filter, and I put coefficients for that filter into B and A. MATLAB has a function called filter, not L filter. L is for linear filter in Python, but same thing as filter in Python. So B are the coefficients in the feed forward section of a digital filter. A are the feedback coefficients. So what do I want to do to stretch this out? I simply want to repeat the samples 10 times. So I'm going to put in 1s, 10, and this is going to be the coefficients in the feed-forward coefficients of my filter. I'm upsampling by a factor of 10, and then I'm going to put 1 in here for the feedback coefficients, saying there are no feedback coefficients. So now let me remove the dots. If I was a magician, I'd say voila or something like that. I now have a waveform. You see what the difference is there? I now have waveform values because that filter has done that. And if you messed it up and made that only 5, now we're going to get a waveform that looks a little bit like a Manchester encoded waveform, but it only has 5 up samples and then it has 0 down samples everywhere else, and that's not what we wanted. If I put in 15, now we're going to get a multi-level sequence. That's not what we want either, because we stretched each bit to last more than 10 samples, so that's not what we want either. We want just 10. So there we have it. So now we could go ahead and Fourier transform that, but I actually have functions in the library. They're actually, yeah, they're in, I forgot, they're in the digital comms module, but they're also in the SS module too. Let's find out. There's NRZ bits and NRZ bits too, so I'm going to go NRZ tab, I'm going to go NRZ bits, and then this is going to be, some of these things are in different modules. They're just simply imported, so they're available depending upon what you want to do. But a lot of these things got put into the SS module, and I don't know if I explained, but SS module, sometimes in the notes I have written still as SSD, and that was because when I wrote the Signals and Systems for Dummies book, my module name was ssd.py. I wrote that for the book. And SSD there meant Signals and Systems for Dummies. My book editor never thought much of it. She didn't appreciate the code that I wrote at all, as a matter of fact. So when I created the Scikit DSP-Com package, we had to get rid of the SSD because I felt like Wiley Publishing really didn't care about my Python code. And I came up with a new name for the module called SIGSys, and then its abbreviation is SS. So it was done kind of intentionally. So SS was originally SSD. At any rate, shift tab on that. This is going to create a bit stream of so many bits and so many samples per bit, and then the pulse can be the rectangle, it can be a raised cosine, or in the case of problem set number 2, it can be a square root raised cosine pulse. And just inherit some of the properties you saw when you were working problem set number 2. So we now have that, and I'm going to say let's do, I'm going to do 10,000 bits, and I want to do 10 samples per bit, and I'm now starting to type and I'm forgetting what was I doing. Hit Shift Tab again and I can bring the help back up and I can see what am I doing. If you were in VS Code doing this, you would get a different form of kind of available help, but Pulse is defaulting to rect, but if I want to just type it in, or better yet, if I type Pulse, let's see, just show you another little PUL, and I hit Tab, it's saying, oh, you must mean that you want to set a value for the pulse type, and I'll just put the default value in there. I'll tell you why you would want to do this. If you're writing code and you're trying to remember what do all these argument values mean, you can think the first 2 are pretty straightforward. How many bits do I want to generate? How many samples per bit? But then your brain starts fuzzing out. So if you do this in your code, type the name of the parameter and then set it to something. When you go read your code later, it'll be really obvious. Hey, I set the pulse shape type to rect. If you want to define the other ones in here too, you can do the same thing. At any rate, and what does this function return? Go to the help, scroll down, the returns, the first argument that comes back is an array of NRZ signal values. Second one is the pulse shape itself, which is useful further downstream when you're building a transceiver simulation. We're not going to do anything with it at this moment. And then the third one is the data bits themselves, because this is going to produce random data bits. So if I want to do error probability checking to make sure I'm getting the correct bits received after I do more signal processing with them, I might want to have access to the actual random bits themselves. So it's just more stuff to have in your hand so you don't have to go back and get it somewhere else. get at it from somewhere else. Before I run this, I think I ought to also tell you that what NRZ does is NRZ is non-return to zero. That's a type of signaling that communications engineers use. It's not the usual logic family logic swing of like 0 to 5 volts or 0 to 3.3 or something like that. It's what's called a bipolar type of waveform signaling, and it's used in electronics for sure. So right now, this guy doesn't abide by that, so let's make it look like that. And what I can do there is I can say 2 times the 0, 1 value, and then I'll subtract 1. So I'll make the amplitude swing go from 0 to 2, and then I'll drop it down everywhere by 1. So now we'll swing -1 to +1. And this is going to make a high or a 1 bit become a +1 and a 0 become a -1. I'm working on the LunaNet project now, and they have it reversed. They have, flipped upside down. So you just got to read your requirements document. So let's do that. So now we have a true NRZ waveform, non-return to zero with rectangular pulse shape. Let's compare it to what we're going to get from here. We're doing 10,000, so let's just plot X. Let's plot 1,000, see what that looks like. There it is. Does it look periodic? Does it look random? I mean, what can your eye make out right now?
Looks pretty random.
Yeah, and it is. I'm doing this on purpose, but okay, let's go down here and let's just repeat this again. Now we're going to use NRZ bits 2. Just my simplicity said let's create another version of this, but instead of putting in the number of bits you want randomly drawn as zeros and ones, we're going to put in a waveform that we choose as data for my NRZ. It's going to be data that switches between 0 and 1, data bits. So the way I load this guy up is I will copy this just for ease in having it copied. And then I'm going to replace that 10,000 with, remember PNGen, I told you exists, and what PNGen does is it lets you say how many bits do I want to create and what PN code length do I want to use. So I'll use a five stager in here. So I'm going to go 10,000 again, and I'm going to say it's from a 5-bit generator. Oops. I use a Macintosh, I use a Windows machine, and guess what? The keyboard commands are not the same, so my brain gets all confused about which keyboard strokes to take. So let's just plot that same guy. Returns the same variables almost, so let's just make sure we know what it's returning. It's returning only X and the pulse shape B. It's not returning the data, because the data was already plugged in right here. So I already know what the data is. So just remove that from the list. And this is with the 5-stage generator. See, it's periodic, or it appears casually. We could do an autocorrelation on it or something like that if we wanted to, random. So let's just go ahead and demonstrate what I was getting at about random bit streams and pseudo-random bit streams, and what does it look like in the waveform. So we're going to use my function PSD, which is the simulation function for doing power spectral density. So we're going to fill in those values, and it returns the power spectral density at the frequency sample spacing that's in the array F, And that frequency sample spacing is based on choosing an FFT length, and then you have to assume the bit rate is, say, 1 bit per second, and then the sample spacing will be controlled by Fs. It will be 1 over the sample spacing in the time domain will be 1 over Fs, and the sample spacing in the frequency domain will be Fs. So let's just take and do that. So we'll just take this first one, and I'm going to have to rerun these cells, make this be X. That's X, XPN. Oops, should have gotten an error message. Oh, why didn't I get an error message there? I already ran it, right? So there's a variable X sitting there in memory already. If I would have started over again, it would have complained. But let's just make sure we get XPN in there, and then let's go up to here and make this one be, I'm not going to use the data, I'm not going to use B, so I don't really need to relabel these, but I do need to make this be XRAND. And we're only looking at a little snippet of each one, but we're going to do a much longer average. So we'll go PX RAND. FX will be the same if I choose the same sampling rate. So here I'm now going to start filling in what I need. I'm going to put X PN RAND, and then I need to choose NFFT. I'm going to go 2 to the 11th to start with, 2048. And then I'm going to choose a sampling rate. Now I have to think. How many samples per bit did I put up? I put up 10. So if I want to keep things in terms of 1 bit per second, I would want to make Fs, my sampling rate, correspond to my 10 samples per bit. Does that make sense? At 10 hertz. So I'd be, and you can scale everything accordingly. We're not really worried too much about that right now, but I'm going to make that be 10. And then the other attributes, I'm going to leave set to their default values. So now I'm going to repeat this. And this will be PN5. And I can make this, these are going to be identical because I'm going to set the same sampling rate. But you want to watch yourself. You might want to have different names for the frequency axis to make sure that if they have to be different, they are different. Oops. Oh, I didn't do PN5 because I was planning on changing it. So I left it at just PN. So now I can go ahead and just plot everything out. I can plot Fx, I'm going to do in dB times log 10. And this is power spectrum. So power spectrum is what? Real or complex? It's real, right? It's the power per unit hertz. So it's a real number. You don't have to worry about an absolute value. And log 10 is what we want because it's 10 log base 10 of a power quantity. So we're going to put in power spectrum PX. Make sure I do the RAND one first. And I could put a label on it. And so I'll do the second one. I know it's taking a lot of time, but maybe this is going to be helpful to just see more cases of typing code. If I put in a label and a plot, I have to put in a legend. So I don't have to put in any arguments into it because it gets managed by what I'm putting into here. If the legend doesn't organize properly, You can always go under Legends Help and see how you can pick different orientations. This is an important one that I use frequently, is I will put in an option to control where it lands on the plot, because sometimes it's smack on top of something that I want to see, so you can organize where it goes. But right now we don't need to do that. So maybe this doesn't tell you what you want to see. First off, what I'm going to do is I'm going to do what I highly recommend, and that is set the limits on y, so I don't see something going down to minus infinity or too far down. So I'm going to take it down to about minus 40, and I'm going to go up to 20. That looks like that should work well. And I could put some grid lines on here. Can't really see all of what we want to see, so we could do a second plot, or let's just look at one at a time. There's the random one. Let's put the grid lines on here. And another little trick that I'll just tell you, since I'm doing all this practice, if I don't put a semicolon on the end, it prints out something associated, like y lim was the last line in the cell, and it's printing out those limits. But if you don't want to see that stuff, you can always put a semicolon on there, and I usually end my cell with something like grid with a semicolon, and then it doesn't print anything extra beneath it. So this looks, it's a little bit noisy looking, because the power spectral density estimator does have that characteristic to it. It has the character that it's estimating just like the sample mean would estimate, or the sample variance would estimate from a bunch of random numbers. It'll estimate unbiased, but it will have some variation in it. So it's a little bit noisy looking, but does it look pretty continuous? We could zoom it, but let's just try that. Let's just do that to see that y lim goes 0 to 1. Let's just look at the main lobe. Remember, this is bits per second, so this is 1 hertz effectively in our modeling so far. So it looks pretty continuous. It has some estimation errors associated with it, and I could drive those down more. I could be really crazy about it. I could take this and I could do 100,000. Really didn't change it at all. It's still got some noise associated with it. So now let's go in and uncomment the PN5. And it has definite spectral lines in it. And to see them more clearly, what we'd have to do is go up to a higher FFT length. So that didn't quite do it either. Let's take this up higher. I'm getting lost in all the code I have here. Let's take this up to 14. Both of these to 14. Okay, now it's looking, now the amplitude needs to go up because of the way the scaling is being done on the PSD display. Let's take this to 40. There. So it's pretty obvious it's spectral lines. It's periodic, right? So what happens if I make the PN generator? Which way do you want to go? Just to make some common sense, I can make the PN code shorter. Right now it's a 5-stage generator. I could go down to 3, or I could go up to 10. What do you want to do? Go up to 10. So it's going to become, the lines are going to get really close together, right? Okay, good thinking. So I'll go back up to this line here, and I'll put in a 10-stager. Looking at a few of the bits, it just looks like now it's 1023 bits long, and we're not seeing enough to see it repeat. But we do know a PN code always has the existence of one pattern of, say, 10 bits for a 10-stage generator. That occurs once in the period. That's a property of a PN code generator. So now, what did I do? I didn't rerun the spectrum estimate. Now it looks very almost continuous. Is it really continuous? So we could zoom way in on this. We go to point 1, and this is similar to what you're doing in the lab. Still don't see anything there. How about 0, 1? Now what we have to resort to is increasing the length to this even higher. We have to make sure the resolution, which is 1 over 2 to the 14th, can even see the 1 over 1023 that we're looking for. So let's take this up to 15. They're starting to become visible. They're not really all that super visible at this point. If we crank this up even to higher, so this is what you do in the lab when you're doing this with a spectrum analyzer. You crank the resolution bandwidth down very narrow, and then you start seeing the periodicities. Where if we go back over to what we started with the random bits over here, oops, I changed something. What did I do? Oh, I didn't take this up to 16. Why did I get that error message? It's because the number of samples in FX doesn't match the number of samples in the spectral density. This is just looking like there's no spectral lines appearing, it's continuous. So the autocorrelation on this, the random sequence is just the triangle, and then just uncorrelated from there on out, either direction. Is that making sense? What do you want to send somebody? Random bits or pseudo-random bits? Pseudo for certain types of signaling, but when you're sending real data, you got to send random, right? You might scramble it in some fashion, but you want to send information from point A to point B. So let's lay these on top of each other, comment this guy out again. So there's our PN10, and just review this again. Take this down to 3. There the pattern repeats very frequently. Run the spectrum again. There's the continuous part, and then there's the discrete spectral lines. And right now the scaling could be changed in the spectral estimator. Right now I have it in the mode for noise. Scale the noise to true. If I was to set that to false, then it would try to make the spectral lines at least correspond to the dB values in power. Right now it's assuming it's a noise-like waveform, so that's why the two of them don't scale the same, because they have a different character to them. I'm going to move into the linear systems after the break, but any questions before we move on? Remember, I have this sign-up sheet I want you to get the email address of Brian Fox, who's my manager at Emergent, if you are interested in interviewing for an internship position. So put your name on here just so I know who's signed in. I don't want you to send me your resume, send him your resume, and then he'll be talking. So you can come up and do that at break time. But any questions on what we've been looking at? I'm trying to weave in digital communications, even though you don't fully understand it yet, but we're going to be doing it in Chapter 3. We're going to be sending analog waveforms and digital, coherent and non-coherent. You're going to see a lot of interesting phenomena about comms. Analog comms is actually the easiest, and it's been around the longest. You know, CB radio or whatever, trucker radio and other such things. Our brains are really powerful. We can hear stuff. But if it's bits, we got to get our act together to get the bits properly organized. Okay, we'll come back at around 9:40 would be nice, 9:43 or somewhere in there. We'll get started again. I'm going to stop the video. Okay, we're back in the second half, and I thought we'd move into the quick overview and walkthrough of linear systems theory and some of the new items that are in for this semester as opposed to what you did in 3205. But there's a couple of other numerical things that are kind of cool to look at. We had looked at modulation theory, and you're going to be doing this a lot in Lab 3, and we're going to be doing that starting in Chapter 3 and Chapter 4. So this was a triangle waveform modulating a carrier, and this shifts the carrier up and down in frequency. Another thing we might want to model is just the duality theorem. If we put a sinc function in the time domain, we should get a rectangular pulse out in the frequency domain. So here, I simply generate a sinc function, implement it in this line of code to exactly match this. I have to pick a time interval of so many periods, and when I do that in here, I've only got so many periods of the sinc function. Remember, this is a band-limited function. The sinc function has tails that go to plus or minus infinity. So when we go and look at what the Fourier transform is, and this is done using the Fourier transform approximation, which hopefully now you're believing it is pretty good. It's based on DSP concepts, but it has this ringing in it, and the ringing is really not acceptable in most common applications of wanting to work something from a sinc function to the frequency domain. So what you have to do, and this is in decibels, you can see more clearly that the first lobe here is down 21 dB, which is not very acceptable. So what you end up doing, at least from the DSP standpoint, is you implement what's called a window function. So in digital signal processing, you have various window functions, and a window function is exactly that. It multiplies the time domain by a function that shapes what's in the time domain, and it's called a window by convention. A simple window is a rectangle, and a rectangle window just does nothing. It just multiplies everything by 1. But in the Python library here, there's a special sub-module within the signal module of SciPy called windows, and so there's quite a number of windows. One that I like using in applications is the Han window. Scandinavian guy, his name is Han, and I'm just telling you a little story because stories are fun to tell about history. His window, a lot of these windows have the names of people. You can see there's 4 names at the bottom there. Well, there's a bunch of them: Hamming, Han, Kaiser, Kaiser Bessel, Lansos, Nuttall, Parzan. All these different people came up with windows for different things, and windows are used in filter design, spectral estimation, and so on. So the Han window was called Hanning for the longest time, and I thought that was just good. Called Han, as in Han's window is the Hanning window, but that was actually an abuse of names. So we got the community cleaned up its act and said it's the Han window because it's in honor of his name. Hanning is like a slang term, which maybe some of you are familiar with slang terms. I went to school at Michigan Tech. A lot of people came from Detroit, so they would say, I work at Ford's, as in F-O-R-D''S, and that's kind of slang sounding too. So they cleaned up the name. I don't know if people would say Chryslers or GMCs, but I don't know. You guys aren't in that community, but if you lived in Michigan, Michigan is very automotive centric. So what I did here is I said, let's just put a Hanning window on here, or a Han window. See, I can't say it right because I've called it Hanning for such a long time. So let's just put that window in here, and let's just make you know what it looks like, what it's doing, it's shaping. So there's what the hand window looks like. Normally in digital filter design, it doesn't have this many taps to it or samples to it, but what it's doing is it's bringing things down at the edges, kind of bringing it back to zero more gradually rather than coming along and just chopping it off. Because we know that chopping things off causes an abrupt change in a waveform, and that tends to give a lot of splattering in the frequency domain. It will give extra harmonics that don't settle down quickly enough. So here I'm just going to put in, engage the hand version of this. If I can see where I put it in here. There it is, X4. Yeah. So I generate the handing window above, or the hand window in here. I'm plotting the regular window, and then I'm going to engage this. And let me do it in both places. Obviously, I made a mistake somewhere. Oh, I got it on comment, another line. So now you can see, at least in the frequency domain part, that it doesn't have the ringing. It has more of a roll-off like you'd expect in a filter. It doesn't jump instantaneously to zero. And it does a great job of getting rid of the side lobes. The side lobes are now down 60 dB or more. Nothing else pops up. So we're not talking about digital filter design in this class, but I just thought I'd point out to you that you can build things in these models that are not physically, realistic. They have artifacts in them. So just something that you have to learn a lot by experience, I feel like. Hopefully that doesn't matter to you in your career. You're worried about that when you interview. I don't know enough. Companies that interview expect a certain amount of something, and they want to be able to train you. Actually, some companies like you to be not overtrained into bad habits that they don't want to see in you for the type of work they do. So they're respectful of the fact that you need to learn stuff, and they want you to be eager to learn it and then get better at things. And you do make mistakes, and you learn by your mistakes. So not that big of a deal, as long as you press onward with enthusiasm. So there's a whole section in the rest of Chapter 2 on linear time invariant systems. I don't really want to spend hardly any time on this, but I'm going to kind of step along and just refresh your memory, things from 3205 that you've had. We have linear time invariant systems. We'll be assuming that we have, throughout the rest of the semester in Chapters 3 and 4, we're going to use filters a lot. And we're going to assume in an initial design that we'll use ideal filters, but then when we do simulation models and other things, we will use some sort of a digital filter or a representation of an analog filter in digital form to make a model for something. And then in the actual implementation, which doesn't get done by us, but maybe in the lab to some extent, in the case of the lab experiments, there's some experiments that have software in the loop of the hardware using an interface to the PC. In other cases, we use the filters that are in the lab already, which are okay. They're not as great as I'd hoped for, that are realistic filters. So we have combinations. And in industry, if it's a software-defined radio architecture, it's almost always a digital filter. But there are analog filters in the system, and I've got a table at the end of this section that talks about filters and different technologies that are used for filters. This is an area that crosses into microwave circuit design and RF circuits in particular. So we have an operator that obeys linearity, so superposition holds, and we're going to assume that a system is time invariant or fixed. That's just logical stuff. We will have nonlinearities here for sure, but linearity just means superposition holds. In time invariance, the bottom line there is something does not change over time. In an analog filter, it's just saying it's going to stay the same. But an analog filter, in reality, doesn't stay the same. Just in case you didn't know, components age, temperature changes, values change. So, but in the short term, we still treat most analog circuits as time invariant. In some instances, in DSP in particular, we have adaptive filtering going on. So that's possible, and I think most of you are familiar at least with adaptive noise canceling. Some of you use that, right? Are you happy with the way it works? By and large, I'm happy with it. It doesn't, if you don't get a good seal on your ear, you don't get as good a cancellation, but it's a powerful DSP technology.
Well, it doesn't make me nauseous, it's okay.
So it has that, it causes that phenomena, okay? Well, I've got a system I worked on in audio, another little story if I can keep it short here. There was 3D audio producing, so I could use my noise canceling headphones and then simulate audio coming in to your ears with a model for your head-related transfer function. Does everybody know that your head has got two transfer functions associated with it, one for the right side, one for the left side? And it's how we learn to hear, and we can walk around and we can hear and sense spatially. It's actually extremely powerful. It's not something you go out and buy, it's something you're born with, right? You're born and your brain gets trained to interact with how the biomimetic sensing works in your head and how you can know if a car's about ready to run you over because it's coming from that side versus that side. I go out running a lot with my dogs, I cross streets. How can you get around without having that capability? It's very vital. But at any rate, in this system I created a thing that would drive the headphones to model, and I worked with a couple students on this for virtual reality was one approach. You need virtual reality in the vision side, but you also need it in the audio side so you can sense. So I created a system that uses an HRTF from a mannequin model to model what my hearing would be. And it works well for me, but you really need a custom one. But at any rate, I can spin sound around your head, and that can make me dizzy. If you sense, the sound is pretty well matched to the way your brain works, and if you start spinning the sound around in different orientations, I can get nauseous feeling because it's a little bit like putting yourself on an amusement ride. So I can relate to what you're saying. Most people found it to be kind of fun because I guess you like roller coasters. I'm not a roller coaster fan, though. At any rate, that's another thing that's kind of fun to do. I think I have a link to it. It's on GitHub from a paper I published. So the impulse response is like the kernel for a linear time invariant system. It tells you how the system responds to a delta function. And that leads to ultimately these two equations here, which are the two convolution expressions for getting the output from an input and the system's impulse response. It turns out evaluating intimately these integrals is not something that's really that important in this class. We bump into it every now and then. We particularly bump into it with the delta function. I used that today, right, where I said let's expand a waveform. In here, I just said, let's take a waveform and replicate it up and down the time axis by convolving using a delta function. And don't ever shy away from a delta function convolution because it's not a nasty, hard one to do. I don't know if Dr. Trimboli says it that way exactly, but it's not one that you get choked up about. What we're talking about right now in this section of the notes, it does get more tedious to do the convolution integral. I don't want you to be fearful of it, mostly because it's not really relevant. The system does it on its own. And the analog system, wow, it's amazing. It does it, right? It's real time. Analog circuits have some really nice properties. You don't have to micromanage how it works. digital signal processing requires a DSP engine and algorithms to be written. So the differential equation just does its thing. And we can simulate it using tools like SPICE. Stability, yes, we want bounded input, bounded output stability. And this is the theorem that you learned in signals and systems already. The absolute value of the integral of the impulse response, or the integral of the absolute value of the impulse response, has to be less than infinity. And in the case of continuous time systems, that just ends up meaning that the poles have to be in the left half S-plane. In the discrete time domain, if it's going to be a causal system, it has to be inside the unit circle. And causal systems are naturally occurring in analog systems, whereas in DSP you can have anti-causal and non-causal systems, but in reality you can't ever go forward in time. So it's just concepts mathematically. Transfer function is the Fourier transform of the impulse response. I think you know that, and it's just the way to get the frequency response. And if it's an impulse response, it allows us to get the frequency response of the filter, and then it allows us to take advantage of this blue boxed equation here, which you grew up in signals and systems a lot. We will be using it in chapter 3 a lot. As a matter of fact, we'll be making assumptions involving ideal analog filters just to prove a concept out. So we'll be using this without hesitation. I mentioned causality. That just says the output relies only on present and past values of the input. In analog systems, that is just the way it is. In DSP, we can run things backwards, like I said, so you can actually have a non-causal system, but you can't really run it in real time, so we have the same problems with real-time behavior. This theorem is kind of exotic looking, but the bottom line is it just says you can't go off and build any frequency response you want. And I'm curious, does this get talked about in 3205? What do you think about it, though? Just saying that it just shows you mathematically that this must be true. And this is a theorem for a causal system. The basic bottom line is that if you're going to try to build a filter that's very band limiting, only passes some frequencies and blocks all others, you have limitations on what you can do in order to make it realizable and be causal. So first condition is you can't block out to zero a band of frequencies. You just can't do it and be realizable. But you can have certain points, like points of ripple and so on, that go to infinite insertion loss. And that's part of the theorem. And you can also control the roll-off rate. So you can have a roll-off rate where, say, n is an integer, like in a Butterworth filter. You can have 60, 70, 80, whatever dB per decade roll-off in an analog filter. Our practical analog filters are Butterworth, Chebyshev, and elliptical. There's also Bessel filters. Those ideas transfer over to different types of digital filters. But when it comes to electronic systems, like for space radios that I'm familiar with, generally they go to even more exotic topologies and design types, and that's talked about a little bit later here. Frequency response is got for real filters that signals that are real go through as opposed to complex. You have an even frequency response magnitude, odd phase. You have an important property here for power signals that have a power spectral density. This is new. The proof of it is actually in chapter 6 of the book, but I'm just asking you to take it on faith that you can utilize it. It just says that the power spectrum at the output of a system is the magnitude squared of the frequency response times the input spectrum. It's just an extension of the basic frequency response relationship. You can go x times y, h of f becomes y of f, and this just extends to the spectral density. idea. And this is how, like in transmitters that I've worked on, like the space radio I was working on, the raw emission is not acceptable by the government regulations, so we have an additional filtering stage to limit the spectral occupancy. And I'll talk about occupancy before we leave today too. So we just end up modifying things with a filter. This is classical. You've seen this, can anybody count how many times I've seen an RC low-pass filter since you started in electrical engineering? It's standard though, right? It's just like bread and butter, comes back over and over and over again. It's great though because it has a lot of analogies. There's a digital filter version of this, which I always think back in my head, 2 pi times RC, time constant, which got utilized a lot in my early career in electronics. You have the differential equation. You have the Laplace transform on both sides. You can do the Fourier transform on both sides. You can get frequency response, magnitude, and phase. And that's the stuff that I have in here. You can look at the pulse response. What happens when I put a rectangular pulse into a RC low-pass filter. Let's see, I've got that in here. So you get this result right here. You've seen this over and over again, but these are things that you have your eyes on all the time. You say, when I send a pulse through a RC low-pass filter or any analog filter, I will get some sort of a response. I'll get a pulse response, and the pulse response is always a finite rise time and then a decay time. And then the action of the spectrum is just shown here for different characteristics of wideband and narrowband filters. These ideas are kind of second nature, though. I'm saying that because you've been through a bunch of classes already. You've been in electronics, you've been in circuits, you've been in signals and systems already. Then I already mentioned this earlier. Actually, I switched it from chapter 6 to 7. I don't know why this changed in the notes, but at any rate, the power spectral density relationship. If a signal is periodic, it goes in periodic, comes out periodic. So that idea holds. This last line here is just the extension for a line spectra going in and coming out of the filter. And these are good concepts to know. They're important concepts to know, that if a sinusoid passes through a filter at a particular frequency, it picks up H at F naught, where F naught could be at a harmonic frequency, and so it's picking up magnitude and phase at that particular frequency. So now something that maybe is new and maybe is not new, distortionless transmission. Oops. Is that something that you can remember from 3205? I'm thinking, did you do distortionless transmission? Because this is a new concept and it's an important concept for communication systems. What is distortionless transmission? Systems that offer a pure time delay introduce no distortion. But what is distortion anyway? If you're trying to listen to some speech and there's all kinds of noise interfering with it, and all that noise lies outside the bandwidth of the speech, don't you just think that I could filter a lot of that excess noise away that doesn't contain speech, and I'm perfectly A-OK? Right? I mean, I do it. So that is a form of distortion overall, but with respect to the signal of interest, filtering away unwanted information is not introducing distortion unless it's in the band of frequencies where your signal of interest lies. So that's part of where the notion of distortionless transmission occurs. So these are the comments. Number one, amplitude. Amplitude response is not constant over a frequency band of interest, then you have amplitude distortion. But if it remains flat over the band of interest, then you're no distortion. Phase should be linear phase at most over the band of interest. And if it's not, then you have phase distortion. In optical communications and in microwave communications, we would say that linear phase is just a constant delay, and I give an example here next. If we have a non-linear phase, then we get what's called dispersion. So we get pulse smearing occurs when that happens, and that's not good. When I first worked in fiber optics, and I got a chance to try that after I did free space optical, I got exposed to multi-mode optical fiber. And multi-mode optical fiber was the early days of fiber optics, where there was a grading of the diffraction across the diameter of the fiber, and it would not carry a wideband signal effectively. But then Bell Labs and other places realized they could come up with geometries and profiles in the design of fibers that would be dispersion-free, and that was what became single-mode fiber, and that's what we use today. That's how our fiber optic cable can carry so much information, because we don't have phase distortion in it. So the third type, so I was just mentioning phase distortion. In digital comms, phase distortion gets into our passband, and it does distort our waveforms, and we end up with both amplitude and phase contribute to what's called inter-symbol interference. So when we send that bit stream that I was showing before the break, a bit that's transmitted here will get stretched out, and then it will interfere with another bit that gets sent down further down the line, and that introduces what's called inter-symbol interference. And what I had you study in homework problem set number 2 was the square root raised cosine pulse shape. And what I will detail out more, I'll detail a little bit just now, but that pulse shape is what's called a Nyquist pulse shape. And the reason why it's square root raised cosine is because we put half the filter on at the transmitter to shape it for transmission with a contained bandwidth. And then when we receive the signal with noise, we filter it again with what's called the match filter. So we do a square root raised cosine, second square root raised cosine, so we have a raised cosine response across the effective TX and RX path. And the Nyquist pulse shape has the property that the squiggles in the pulse shape all cross through zero from adjacent pulses. So that means that we have inter-symbol interference-free communication. We can transmit a very narrowband pulse, but the ringing on the pulse is such that adjacent pulses don't interfere. Does that sound exciting? To me, it was an innovation. You know, Bell Labs was part of it, of course, because Bell Telephone had to deal with that in wired analog telephone lines, too, that were sending digital. But so that's an innovation, and it's very important. Third is nonlinear. And nonlinear, from my estimation, is just all around us, too. When we do digital, we just want to send ones and zeros, but when you build an amplifier to transmit a signal, you have to worry about falling outside the linear operating region of a device. And you study this in electronics to some extent, but you know, say a FAT or transistor amplifier does not have a pure linear response. It's been approximated to have a linear response, but then it has a higher order terms, and that's what this deals with. And I'm going to give you a homework problem on this for sure in the next assignment. And I'll try to demo that before we leave if I get a chance. Group delay is a measure of the phase distortion. So group delay is taking the derivative of the phase response, dividing by 2 pi. And group delay basically comes down to the idea that if you send a signal at 2 different frequencies, does the phase shift between those 2 signals, or back up and say that 2 frequency, you can come up with a delay distortion, but if you want to be truly constant group delay, you want all frequencies, not just 2 frequencies, but all frequencies to receive the same delay. So that way the whole pulse, which occupies a spectrum of bandwidth, gets distorted by the same amount at all frequencies. So the pulse maybe rises and falls slower, but it doesn't get sort of smooshed out into a distorted mess. So that's what delay distortion is all about. And group delay, because it's a derivative of phase delay, and phase delay that's distortionless is just a linear phase delay. So when you multiply it, take the derivative of it, you just get a constant group delay. So constant group delay is what we'd strive for in the band of interest for a digital comlink in particular. Our ears are not extremely violated by non-constant group delay. If you're a musician and if you want to hear all the overtones in an orchestra blend properly, you don't want to have some overtones get delayed differently from others, because that's going to cause phasing and that's going to not make it sound natural. But if we're talking about speech, we can tolerate a lot in speech. Digits, we can't tolerate a lot. We're more likely to cause bit errors then. So I kind of go through an example, but I'm looking at the clock here and I'm saying this is about all I want to say right now. The bottom line is we want to have a constant group delay. And if we can't get there, we have to build a compensator for certain high-power microwave filters and things that are used in SATCOM. If we're doing it in DSP, we can design linear phase FIR filters, and they do what we want them to do. So we have ways around it. Most modem-type people will use everything that's good and proper for a constant group delay in the band of interest. And if the RF power people have to build microwave filters, they may have to compensate them to make sure that they don't introduce delay distortion. So a simple example is a transmission line. I used to teach microwave circuits. I actually developed the class that Dr. Song took over when she came. And the ideal transmission line looks like this. It has a medium with a characteristic impedance R0. It has velocity of propagation VP. And if you properly source your signal in on the characteristic impedance and you properly terminate at the characteristic impedance, the wave travels down the line. It doesn't bounce off. It gets absorbed into the load, and you just get a pure delay. So you get this equation right here. It's just going to be delayed by L, the length in meters, divided by the meters per second velocity. It's wonderful, right? But it's a model, and it's not perfect. So a real transmission line will have some dispersive properties associated with it, and it will even start to mess things up. Now the book likes to go through this example of saying, let's come up with a fictitious system that has this property. And so here's amplitude, phase, and here's group delay, and here's different considerations we might put on this. So I'm going to take and just look at this briefly and say that if you look at this top system that maybe doesn't pass anything above 50 hertz, or 20 hertz I mean, and then passes things with some attenuation from 1 to 2 and nothing between -1 and +1, we'd say that in the green region it's distortionless. If we send a signal that occupies more than this ±1, it's going to receive some amplitude distortion. And then if you look at the phase is perfectly linear if we go from minus to plus 15, but if we go outside 15, we see the phase not being linear anymore. So that's not acceptable. And then if you look at the group delay, you see the group delay is constant over the entire band, but if we go outside plus and minus 15, we have a non-constant group delay or maybe a sloping group delay. So it all kind of comes down to how you want to apply the definitions. And if the most stringent condition is the amplitude flatness and nonlinear phase or non-constant group delay, which are related, remember these two are related through the derivative or the integral, then you quantify, where is it distorted or not distorted. So you have to work with a narrower band if you want to do that. You have to look at a lot of different conditions. I like this example because it's telling you what the definitions are, but how do you practically deal with this? you work in the lab with, say, a microwave network analyzer, and you make measurements of magnitude and phase, and then you can get group delay from that. And I'm trying to think, didn't I have you do that in Lab 1? Did you do group delay in Lab 1? Okay, I'm thinking it's done somewhere, but I can't remember anymore because the lab is in generation 3, and I wrote 3 different versions of the lab, so I don't remember if I had you do that or not. But so last one, nonlinear distortion. And this one, I'm pretty sure this is like almost the end of the line for me for the day. Nonlinear distortion is the simplest way of thinking of it is as a power series nonlinearity. So power series nonlinearity would be if we're staying in the linear region of the operating point for our device. If it's an amplifier, we will get just this condition. We will just get some constant times the input is the output. If we go up to the next power in the power series, we'll get a smaller component of the signal squared, and then we can go on and on from that, cubed, 4th, 5th, 6th, and 7th, and so on. If we drive anything hard enough, we'll push it into the saturation. And you've all done that in electronics, I think, right? You've built an amplifier, and haven't you watched what happens when you push it too hard? It starts clipping or starts limiting. Everybody seen that? So in communications waveforms, we're very worried about that. If you're doing karaoke, because that's an example that I'm fond of from my book. If you're doing karaoke and the karaoke singer gets to be too loud and the amplifier can't support the karaoke singer, what's his or her voice going to sound like? Kind of splatted and clipped off, right? Distorted. So that's because the amplifiers can't handle it. So here we're just taking a 2-term approximation, and what the homework problem is going to do is have you explore a 3-term approximation. But this, or maybe it's cubic with 2 terms. That's what it is. The homework problem will be a cubic version of this. This is just taking you up to the square. So when you go up and work with this, you end up, if you take into account just first order and second order with 2 terms, you get all these components coming out. So what I'm going to have you do in the homework is just a 3rd order version of the 2 tones, but it can go on and on and on from there. But in the case of 2 tones and just looking at what linear and second order does, and then you will look at linear, second order, and 3rd order distortion. What does that do? So we get all of these terms, and what I like to think about is what goes on in the spectral domain, and that's kind of what relates to the characteristic of the distortion. A single tone will get the tone we want at F1, but then the second order harmonic distortion is going to produce a DC term and a double frequency term. That's because cosine squared gives you 1/2 plus cosine of 2, twice the frequency, right? If we put 2 tones in together, though, things start to get messier. We get all the same things on the individual tones. We'll get an F1, we'll get a DC piece, and we'll get a 2F1 piece. We'll also get F2 at F2, a DC piece, and a 2F2. But then the cross term involves the F1 term and the F2 term, and that's going to get the trig identity with the sum and the difference in it. So we're going to get a difference frequency, and we're going to get a sum frequency. And that's only the beginning. All the other harmonics are going to get even more intertwined when you go up to more than the second order. So what we have names for these terms. Harmonic distortion is what happens when we get harmonics of the tones, F1, 2F1, 3F1, and so on. The intermodulation terms are what happens when the 2 tones interact with each other. So we get the minus term and the sum term. When you go up to the 3rd order, we get even more things going on. When we take it to the power of 3, we'll get intermodulation terms, and intermodulation terms in radio systems, especially the 3rd and the 5th order, where we had 3rd power and 5th power, are devastating, because always what happens when we have 2 frequencies close to each other and we take 2 times 1 plus or minus the other tone, it will land in the same band. It's going to land nearby that one. And that intermodulation means that a signal, an interfering signal, can be formed as a third signal right in the band of interest. And does that sound like fun or bad? A friend of mine worked, a company I worked for, Paracle Communications, did a lot of this intermod stuff up in Denver with police, fire, and other radio services. And it's the intermodulations that would send a signal that's a combination of other signals into the same band, and that would drive the police department, fire department, ambulance, whatever, drive them crazy. And he actually told me ages ago that something called passive intermodulation was the most thwarting. Electronic devices will create the power series, first, second, and third order, and so on. But an antenna or a tower that has rusty bolts and hardware on it can actually create some galvanic action between that fitting, the metal bolt being tightened, that when RF hits that structure, it will actually produce the intermodulation. So he would be climbing on towers and looking for loose hardware and things, maybe had rusted or something, and an intermod between strong signals would get generated that lands in the same band just due to what he called passive intermodulation. I know as a person that likes to write software, and you guys probably like to play on the computer, would you think about that? You know, and all of a sudden it's happening. And he was a guy that would go out there and take measurements. He would use a field fox and other instruments like that and try to figure out what is going on with spectrum analysis, how these intermods are being created. So if you're doing the intermod with power series again for a continuous spectrum, you can use the multiplication theorem, so you can get, in this case, this is what happens when you have a signal that's going through a nonlinearity. It's just getting squared. In a linear term, you're going to get the signal itself. Signal times itself creates a convolution in the frequency domain, so your spectrum ends up looking like a little house of sorts. So what am I going to have you do, since you'll be looking at this before we meet again? I'm going to go look. There's a lot of tools out there, but one of the tools that I like using is Wolfram Alpha. Has anybody not used Wolfram Alpha in their life? So all of you have used it, right? Do you like using it? No? But if you got a reason for it. So let's just take an example, and this is just one idea, but cosine of f1 plus cosine of f2 raised to the second power. This is not the only way you can go about doing this, but Wolfram Alpha will give you a lot of stuff, but it's the reduced trigonometric form that tells us what's going on. And this is all it's going to take to work this homework problem. And I'm not going to do it here. I'm tempted to do it. Here's what we were looking at, though. Here you see f1 plus f2, 2 times f2, f1 minus f2, 2 times f1, then you get DC component. So suppose you wanted to go after the third order intermod. Just put a 3 in up here and run it again, and you'll get the answer. But if you wanted to be more sophisticated, you'd go looking on Google. You type intermodulation distortion, intermodulation calculator. You'd be drawn to that, right? Calculator. So there's various tools out here that can do this, and you might want to investigate some of these. They sell a lot of advertising. This one was not, of the ones I looked at, this one wasn't the most easy to use, but there are examples of how to do this. People work with this stuff all the time. They will work with radio design, which we'll be getting into in Chapter 3, and making sure the intermods don't land on top of each other. Make sense? I mean, why create a problem if you can calculate ahead of time to know I'm going to be mixing and up converting and down converting, which is, again, part of Chapter 3. let's avoid the problem before it happens. The problem is my friend was dealing with a tower that hosted transmitters and receivers for base stations from maybe one fire department, one police department, and maybe another one. So now the radio frequencies are not within the control of the owner of the tower, and they end up creating problems that only happened under certain scenarios. So he would drive around, like on E470, for example, thinking about driving around Denver on E470, figure out why are these two safety radios interfering with each other. So track down which tower is creating the problem and things of that sort. Ideal filters, talk a little bit about them. We will be using them in our models a lot. We'll talk about an ideal low pass. We won't typically talk about the phase. We'll talk about the shape of the band pass or the low pass filter as being bandwidth B. We'll consider high pass filters, but we'll talk even more about band pass filters. So we'll talk about band pass filters and low pass, occasionally high pass filters. We'll focus mostly on just what is the amplitude response ideally. We will skirt around the issue of the fact that, say, for the ideal low pass filter, we can't build it. We have a sinc function. Inverse Fourier transform of the rectangle is a sinc function. We were looking at that already today. But we still will use that as a concept when we're designing something with block diagrams and things. We'll want to see, does an ideal filter make this work? If an ideal filter doesn't allow a system concept to function, a real filter is not going to work at all. So we have to at least start somewhere. So we'll be using these types of filters, the ideal filters, a lot. We have realizable filters, Butterworth, Chebyshev, elliptical. Those are talked about in the book. They're in the Python libraries, as a matter of fact. Let's just go over here to make sure. Do I still have this up? If I was to go into Scikit DSP-Com, for example, there's this module called FIR Design Helper, and then the IIR Design Helper. Both of these modules, which are in your Scikit DSP-Com, either were written by me standalone, or they are built on top of what the scipy.signal module has. So we have those available, and it will be using these filter design tools in some of the models that you'll build later on. Last thing I think is going to be this, and there are examples in the notes. There's examples in the notebooks. These are some various technologies. In the lab, you've been exposed to LC passive filters, active filters. You built active filters in electronics, right? Crystal filters. We have ceramic filters in the radios that are used in the lab. We have SAW filters. Did I mention SAW filters? Surface acoustic waves. I know I talk about them in modern DSP, but SAW filters are used a lot too. If you can believe it, you can have a substrate that rather than carrying an electromagnetic wave across the substrate, like in microstrip or so on, you actually have a substrate where you set up an acoustic wave that goes along, and you have interdigitated metal fingers, and a wave can get launched, and then it gets tracked by another set of fingers, and the interaction with the acoustical wave on the surface allows you to build a filter. And that's a useful technology. And in these bands, we have transmission line-based filters built with open and short circuit stubs, coupled lines. And then for the high power microwave area, like in satellites and things, we go with cavity-based filters, which are machined and plated metal to do certain bandpass filter implementations, including things that compensate for delay distortion. Last thing I'm going to talk about in about a minute or two is just an issue that came up in some of the papers I've been grading, slowed me down, irritated me a lot, and I can't read because it's in microprint. I talked about this earlier, but not all of you were in here. One paper I was just grading, sentences go on like that long, and then if I look at it, it's like the size of the pencil tip on my Apple Pencil. So if I zoom in on it, I can see it, but then the sentence is just, I've got to scroll all over the place. The way you should be doing things, though, just very simply put, if we're going to a notebook, so let's just take what we were working on here. Let's just take this guy. Suppose I'm happy with this and I want to get some PDF out of this. I might want to put some line breaks in here in the PDF. So the easiest way to export out of this is to go to Save Notebook, or not save and export notebook, export it to HTML. So now it's in HTML, like that. And then I can just say Control P. I want to print it as a PDF. And I'm going to say Save. And I'm going to say on my desktop. And I'm going to give it a name. Random PN. There it is right over here. I did it for chapter 2 earlier before I came to class. Here it is for random PN. This did not come out right. What did I do wrong here? Let's look at the one I did earlier. Yeah, I skipped a step or did something backwards on there, but this is what I did earlier. I wrote it to HTML and then I printed it as a PDF from the HTML, and it just looks, if you separated this with page breaks, which I told you how to insert into your Jupyter Notebook, do you remember me doing that? You can then get an isolated PDF page that you can then print, and then you can merge it with your others or paste it into Word, whatever you want to do. But there should be no situation where the sentences are running on like 3 pages wide. Whoever did that, and you'll read it because I've already scribbled a lot in your paper, it shouldn't have to come out looking like this. I don't know what happened. But obviously I did something on this that wasn't right either. Any questions on that, on production side of things? I did something wrong on that one, though. Okay, now it's working fine. I don't know. It wasn't printing properly. Now if I say this is PDF, this will come out right. Any more questions since we're out of time? I'll see you guys up in lab, and we can carry on with any discussion up there as need be.